Alright guys, good evening everyone. Good evening everyone. Good evening everyone. If you are online, please indicate your presence that you are online. We are about to start. Good evening everyone. Electrostatics. Electrostatics physics. So if you are online, please indicate your presence that you are online. If you are active, indicate your presence that you are active. If you are active, indicate that you are active. If you are active, just indicate that you are active. From the comment section, indicate that you are active. From the comment section, indicate that you are active from the comment section. All right, we shall start because we are already behind time. This class is meant to start by 8 p.m. This is already past 8. All right, so we shall be looking at electrostatics in physics. Some of you already have an idea on this topic, but the course content for tonight, we shall be looking at what is electrostatics. What is electrostatics? What is electrostatics? At the end of this class, you should be able to understand the concept electrostatics. You should be able to understand the concept electric charge. Electric charge. You should be able to understand the types of electric charge. Types of electric charge. You should be able to understand the properties of electric charge. The properties of electric charge. All right. Then you should be able to state Coulomb's law. Coulomb's law and action and direction. Action and direction of Coulomb force. These are the course outline for tonight. We shall be looking at this tonight. But please, if you're online, indicate your presence that you're online. Indicate that you're online. And once you come, once you join us, ensure you share the link to your WhatsApp platforms to invite people. Now let's look at the word electrostatics. From the word electrostatics, electro is from the word electricity. Static simply means rest. So we hear the word electrostatics. Electrostatics is a branch of physics that deals with the study of charges at what? At rest. Electric charges at what? At rest. It is a branch of physics that deals with the study of electric charges at rest. All right. Electric charge, we know fundamentally can be grouped into two. Electric charge can be grouped into two. We have what we call static charge, and what we call current. Under static charge, this is where the concept electrostatic comes in. Electrostatic comes in. Then under current, this is where electric current comes in. electric current comes in. Okay, both of them are branch of physics. Electrostatics talks about the study of static charges or the study of charge at rest, while electric current talks about the study of charge in motion. From the word current means flowing, all right? It means movement, all right? So when you hear the word electrostatic, it talks about a branch of physics that deals with the study of static or charges, or that studies charges at what? At rest. That is what electrostatics is all about. But you must understand that electric charge can be classified into two. All right, we have what we call static charge and currents or electric um, currents. Under static charge, we have electrostatics, which is um, electric charges at rest, while under electric current, we have electric charges that are in motion. It's like the movement of electric current through a metallic conductor from one point to another. All right, like the movement of electric current from the wire to the bulb. All right, such current is called electric current. This such kind of phenomenon comes in under the charges in motion. But when it comes to charges at rest, we are talking about the concept called electrostatics. So that means throughout this topic, we shall be looking at electrostatics, meaning charges at what? At rest, not charges in motion. Okay. From electric current, we know that current is given as charge over time. When uh, if we are to define electric current, it means the flow of electric charge through a metallic conductor over a given period of time or per unit time, right? But when it comes to statics means the study of charges at rest. I want you guys to understand this concept. So that's where the word electrostatic comes in. Electro means it means electricity. Static means at rest. Now we now understand what is electrostatics. Please, if you're online, indicate that you have joined us, indicate that you have joined, indicate that you have joined. All right. So we have seen the definition of electrostatics, which is the study of charges at rest. Please make sure you share the group link to your course mates. Share and like the video. Please, let's be active. If you are hearing me, say that I'm hearing you. Okay. So in essence, that means we have two types of electricity. We have static electricity and we have current electricity. We have static what? Electricity and we have current what? Electricity. In case you are asked to give the two types of electricity, we have static and we have what? Current. When you hear the word static, it means at rest, while current means in motion. All right, just like the concept under friction, what we did, the topic in friction, that was last semester. We talked about the two types of friction. We have uh, the dynamic friction, right? And we have what we call the static friction. Exactly. Static means at rest. When you hear the word dynamic or kinetic, it means in motion. So likewise, this under charge, under electricity, we have two types of electricity. We have the static and we have current. What then is electric charge? Now, electric charge, we have seen that can be grouped into two, either static or what, or current. But by definition, electric charge is a fundamental property of matter. It is a fundamental property of matter, all right, that causes matter to experience a force when placed in a field. It is a fundamental property of matter that causes matter to experience that causes matter to experience a force, which is electric force, right? When placed in an electro when placed in a field, when placed in a field. when placed in a field, when placed in a field, or when placed around a charged matter. All right. So when you hear the word electric charge, it simply means it's a fundamental properties of matter that causes matter to experience a force when placed in a field, or when placed in a charged matter, or when placed in an electromagnetic field. All right. Now that is just all about this. Now we have two types of electric charge. We have two types of electric charge. There are two types of electric charge. Types of electric charge. Okay. Now we have defined the word electrostatics. We have defined the word electric charge. Then the two types. The two types of electric charge we have what we call the positive charge. Positive charge. All right. Number two, we have the negative charge. Right. The negative charge. These are the two types of charge. We have the positive, the negative. We also have what we call, in case they say give the three types, then there is one called the neutral charge, right? Neutral charge. But basically, in some exam, they will just tell you give the two types of what of charge. So what you just mentioned is positive charge and what negative charge. What if they say give the three types, it means they are now requesting for neutral charge. Now, what's a positive charge? A positive charge is a charge that is electron deficient. Electron deficient. Electron deficient, meaning they lack electron. When you hear the word positive charge, what comes to your mind is proton, right? This is a charge carried by what? Carried by proton. Or we can say this is a charge that are electron deficient, meaning they lack electrons in them. An example of positive charge is what? Proton. Proton is a good example of a positive charge. Then when you hear the word negative charge, what comes to your mind is electron. Electrons. What are negative charge? These are charges that are electron rich. They are charges that are what? Electron what? Rich. Meaning they have electrons in them. So they are called negative what? Negative charge. Then we have a neutral charge. These are charges that the number of positive and negative charge are what are equal. Right? That means a neutral. An example of a neutral charge is what? Is neutron, right? Okay. Where the number of positive and negative charge are the same. That's called a neutral what? Charge. All right. Now, there's something else I want us to understand is that whenever a body or a material loses an electron, meaning that the material becomes what? Positively charged. Any material or any object or a body that loses an electron, the material becomes positive charge. Any material that accepts an electron becomes what? Negatively what? Charged. Any material that loses electron becomes a positive charge, while the ones that accept electron becomes what? A negative charge. Let me give an illustration with what I just said. I'm going to use the principle called electrostatic induction, electrostatic induction rather, electrostatic induction, induction, to explain this principle I just said. I said when a body loses electron, it becomes positive, right? But when a body accepts electrons, it becomes what? Negative. Now, if I have a comb, we all know a comb. Let's say I have a comb. This is a comb, for instance. This is a comb, and I rub the comb with my hair. Okay, I rub the comb with my hair. Now, when this comb is being rubbed with with the air, what happens is that the air transfers what? Electron to the comb. Don't forget that any material that accepts electron becomes negative, right? Now, when the comb is being rubbed with the air or with any material, the comb receives the electrons from the air, while the air becomes what? Positively charged. So we are assuming here that after rubbing the comb acquires what? An electron. I want to show the principle of electrostatic what? Induction. I know you must have asked yourself, why is it that after rubbing the comb, I use the comb um come, maybe you bring the comb rather close to a piece of paper, that the comb will be able, the paper rather will attract what? The comb. Now the principle here talks about electrostatic what? Induction. Why is it that after rubbing the comb and we place the comb near a piece of paper, the piece of paper get attracted to what? To the comb? It's simply because, let's say if I have a piece of paper here, this is the piece of paper, right? And this is the charge comb. After rubbing the comb with the air, the comb acquires what? Negative what? Charge. The comb has electrons in them. Are you there? But a piece of paper has an equal number of electron and what? And proton, meaning it is neutral. It's neutral, right? Neutral does not mean that there is no electron, there is no proton. It means that the number of electrons and what? That of a proton are what? The same. So before this comb is actually brought close to the piece of paper, the electrons and the proton are what? Are both equal. Plus, minus, plus, minus, plus, minus, plus, plus, minus, plus, minus, plus, minus, plus, minus. Just like that, okay? Just like that, just like that, just like that. Plus, minus, plus, minus, plus, minus, plus, minus, just like that. The number of electrons and protons in a piece of paper is actually the same. So when this comb has been given the electron by rubbing the comb with air, with human air, either the comb acquires one electron. Now, when you bring the comb closer to the piece of paper, don't forget that the electrons and the protons in this piece of paper are the same. Either meaning the piece of paper is what? Is neutral. Is practically neutral, meaning the number of electron and proton are the same. Now, as this comb is coming close to the paper, what happens is that the electrons here will knock off the electrons in this piece of paper. Don't forget that unlike charges repels, right? Meaning negative and negative will repel. Positive and what? Positive will what? Will repel. So as you are bringing this comb closer to this piece of paper, the more you bring them closer, the more the electrons is being knocked off. Meaning that the electrons here will repel. Do you get the concept now? Now when the electron repel, only the proton will be found somewhere close to the what? Somewhere close to the edge of the paper. The electrons will be somewhere here. When I say knocked off, does not mean that the electrons disappear. Electrons did not vanish. They did not vanish. What just happened is that there's the rearrangement. There's a what? A rearrangement of these charges. All right. So the electrons in this comb knock off the electrons in the piece of paper, leaving behind only the proton here. So as this comb becomes closer to the piece of paper, it attracts, because negative will then attract what? Positive. This is the reason why after rubbing the comb and you place the comb close to a piece of paper, what just happens is that the electrons here rearrange. Sorry, the charges here rearrange. The electrons is being knocked off, okay, to one side of the paper, leaving behind the positive charge at the edge of the paper, which enable the comb to be able to attract what the piece of paper. And don't forget that after a while, it will fall back because this charge called electrostatic charge is not a permanent charge, it is a temporary what charge. So what does happen here is what we call electrostatic what induction. Electrostatic induction. All right. So this is what I'm trying to explain. Now we have seen what is electrostatic. We have seen the two types of electricity, which are static and what current electricity. And we have also seen what is electric charge, which is the fundamental properties of matter. All right. Then we have also seen the types of charges, which are positive, negative, and neutral charge. I will say that positive charge, these are charges that are electron deficient. An example is what is proton. Negative charge, these are charges that are electron rich. A good example is what is electron, while neutral are those body or charge that have equal number of proton and what and electron. And we have also seen electrostatic induction, which I just displayed with the use of a comb and a piece of paper. All right. Okay. Then the next is let's look at the properties of what electric charge. The first property of electric charge. The first property of electric charge. The first property of electric charge is that like charges repel while unlike attracts. Please, if you are following, indicate that you are following from the comment section. Please indicate that you are following from the comment section. Indicate. If you are following, indicate that you are following. If you are active, indicate that you are following. Indicate that you are following if you are following. Okay, so the first properties of charge says that like charge repel, while unlike charge attracts. Like charge repel, while unlike charge attracts. Number two is that charge can never be created nor destroyed, but can be transferred, not transformed, but can be transferred from one point to another. Number three is that charge exists in discrete units. Called quanta. In discrete units called quanta. Okay? Meaning that charge is equals to NE, where N is a whole number which can either be 1, 2, 3. Alright? Charge exists in discrete units called quanta. The fourth one is that total charge of a system is the sum of all individual charge in the system. Total charge of a system. Total charge is the sum of all individual charges in the system. Individual charges in the system. That is, Q total equals to Q1 plus Q2 plus Q3 plus Q4 plus Qn. The total charge of the system is the sum of individual charges in the system. The first one is that like charges repel, while unlike charges attract. Number two is that charge can never be created nor destroyed, but can be transferred from one point to another. We cannot create charge, we can't destroy charge, but we can transfer it. Like we saw, that charge can be transferred from the air to the comb, right? From one point to another. And there are three modes of transfer. We have either by friction, either by conduction, or by induction. Like we just saw between the comb and the piece of paper is called by induction. By induction. Induction means without without contact. There's no contact. All right. Conduction means there must be a contact. Friction means there must be a contact. Friction, when you rub two material together, okay, which can either be an insulator, maybe between two insulator, there can be a transfer of charge. Okay, so that is just that. So charge cannot be created nor destroyed, but can be transferred from one point to another. Charge exists in discrete units called quanta, meaning they exist in a fixed amount. They exist in a fixed amount, and the charge is given as NE, where N represents a whole number, meaning it can be 1E, 2E, 3E, right? But it cannot be fraction. We can't have N. We can't have N as 1.5. We can't have N as 2.5. Or we can't have N as 1 point something, 2 point something. It must be a whole number, like 1, 2, 3, 4, 5, 6, 7. So it exists in discrete units called quanta. Quanta means a fixed amount. A fixed amount, all right? Where E represents 1 electron, represents 1.6 times 10 to the power of minus 19 Coulomb. Our E represents 1.6 times 10 to the power of minus 19 Coulomb. So we can either have 2E, 3E, 4E, as the case may be. The total charge is the sum of all individual charges in the system. If I have a body like this, let's say I have a system of multiple charges. Let's say I have minus 3 Coulomb. Okay. Let me use minus 3 microcoulomb. Let's say I have 4 microcoulomb. At this point, I have 5 microcoulomb. All right. Let's say I have here to be minus 4 microcoulomb. Then here we have here to be 3 microcoulomb. Now, and we have to find the total charge in this system. The total charge is the sum of all the individual charges in the system. Meaning my total charge will be what? Minus 3 plus this, plus this, plus this, plus this. I'm going to sum up everything, which is my Q1 plus Q2 plus Q3 plus Q4. Let's say this is our Q1, this is our Q2, let's say this is our Q3, this is our Q4, and this is our Q5, right? So plus Q4 plus Q5, right? What do? Is to add up everything. By the time we add up, look at this. Minus 3 microcoulomb plus 3 will give us 0, right? When you add up this with this, the answer is 0. When you add up this with this, the answer is 0. So the remaining charge becomes what? Our Q total becomes what? 5 microcoulomb. Is that clear? And charge here, microcoulomb is same as what? 10 to the power of minus 6 what? Coulomb, right? The word micro means 10 to the power of what? 6. Micro means 10 to the power of 6. Milli means 10 to the power of what? Minus 3. Nano means 10 to the power of what? Minus 9. Pico means 10 to the power of what? Minus 12. We have different conversion, all right? So for this micro, this simply means what? 5 times 10 to the power of what? Minus 6 what? Coulomb. This is just what we mean by the third property of charge that says that total charge is the sum of all the individual charges in the system. Is the algebraic sum. Algebraic sum, meaning we just have to add them together to get a total charge. Now let's move into what we call Coulomb's law. Please, if you are following, indicate that you are following. If you are following, indicate that you are active. If you are following, indicate that you are following. Please indicate. I hope the video is clear. Indicate. Okay, so let's look at Coulomb's law. Coulomb's law. All right. Now listen. Coulomb's law is a law between force of attraction or repulsion between 2-point charges. Okay, like we saw between the comb and what and a piece of paper, right? For the comb to attract, to drag the piece of paper, there is a force of attraction that occur. Is that clear? So Coulomb's law established the strength of the force that exists between 2-point charges, okay, separated by distance what? R. The strength of the force of attraction or repulsion, which is called the electrostatic force between 2-point charges, which can either be positive, 2 positive charges, or 2 negative charges, or 2 unlike what? Charges, right? Now listen, the force is that if I have 2-point charges separated by distance r, there are 2 fundamental law of Coulomb's. Then I'll then give the general law that guides what Coulomb's. Please pay attention. Now, we have seen that if we have 2 charges separated by distance, there exists either a force of attraction or repulsion. The first law, the fundamental principle or properties of charges, says that like charges repel, unlike charges attracts, right? So if I have 2-point charges, meaning 2 charges at rest, when you hear the word point charges, don't forget that we are talking about electrostatics, which is the study of charges at rest, right? And the forces that act on those charges. Okay? When you hear the word electrostatic, it means the study of charges at rest and the forces that act on those charges. So if I have 2 charges separated by distance, we can study the force of attraction or repulsion, the strength or the size of this force of attraction or repulsion between these 2-point charges, right? So the first law of Coulomb says that the force of attraction, which is called the electrostatic force, right, of attraction between these 2-point charges, P1 and Q2, is directly proportional to the product of their what? Charges. I repeat again, the force of attraction or repulsion in brackets, which is electrostatic force, right? Okay, between 2-point charges, Q1 and what? Q2, separated by a distance r. Okay, That force is what? That is proportional to the product of what? Of their charges. So I'm saying that, let me write so that we can get the concept here. The force says that the electrostatic force, right? Electrostatic force, okay, between 2-point what? Charges. 2-point charges is directly proportional to the product of the charges. Product of the charges. Meaning that force is proportional to what? Q1 what? Q2. This is my equation 1. By the time I take off this sign of proportionality in mathematics, this is a direct relationship, right? I'm going to introduce a constant, meaning my force is equal to what? K, Q1, and what? Summary? Q2. That means from here, our K becomes what? Force over what? Over Q1 and Q2. Which I can also say this is same as FA over FA1, sorry, FA over QA1 dot QA2 equals to FB over QB1 dot QB2. Just take note of this. Now the second law, like I said, I'm going to give the two law, then give the general law. You all know. Some of you already wondering, this is not what I was taught. This is not what I knew. But just take calm. Just follow the class, okay? At least just add this new knowledge to what you have learned before from your tutor. So you have seen the first. The second says that electrostatic force between 2-point charges is inversely proportional to the square of the distance separating the two charges, to the square of the distance separating the two charges. Meaning from this same diagram, we are saying that force is what? Inverse proportional to what? 1 over what? R squared. So from here, I can take off this sign again, right? This is my equation 2. I can take off this sign and put our equal sign, and also introduce the constant divided by what? R squared, right? From here, our constant K becomes what? F R squared, which is same as F1 R1 squared, right? Equals to what? F2 R2 squared equals to equals to Fn Rn squared. Just like we did here, we are repeating the same thing here. So this is the first and the second. Then the combination of the first and the second will then give us the general Coulomb's law we all know. Now, I will combine these two together to form the general Coulomb's law. The general Coulomb's law. General Coulomb's law. We all know. The law states that the electrostatic force between 2-point charges, right? Q1 and what? and Q2 separated by a distance R is directly proportional to the product of the charges, product of the two charges, and inversely proportional to the square of the distance separating the two charges. Now, what you notice now, we combine the first and the second to do what the general Coulomb's law. The law states that the force of attraction or repulsion between 2-point charges Q1 and Q2 separated by a distance R is directly proportional to the product of the two charges and inverse proportional to the square of the distance separating the two charges. Now, what is the implication of this law? What is it saying? What are we saying here? The law is saying that force, for the first equation we generated, that force is proportional to what? Q1 and what? Q2, equation 1, right? The same force is inverse proportional to what? 1 over what? R squared, equation 2, right? By the time we combine these two, what is common here is force. So that means I'll pick force. Then bring out what is common again, our sign of what? Proportionality. Then multiply Q1, Q2 by 1 over R squared. That will give us Q1, Q2 over what? R squared. This will give us the third expression, right? Therefore, for we to define this force, I have to introduce a constant, right? And an equal sign. That will give us what here? Force equals to what here? K, Q1, Q2 divided by what? R squared. Where K is a constant, which is same as 1 over 4 pi permittivity of free space. 1 over 4 pi. This means permittivity of free space. We are considering air as a free space, all right? And this K here is equals to 9 times 10 to the power of 9 Newton meter square per Coulomb square. Newton meter square per Coulomb square. The value of our K is 9 times 10 to the power of 9 Newton meter square per Coulomb square. So this is the general Coulomb's law. The general Coulomb's law. Okay, so please, if you are still following, indicate that you are following. If you are following, indicate that you are following. If you are following, indicate that you are following. Can we proceed? Now we have seen Coulomb's force, right? Coulomb's force. The force says that F equals to what? Okay, Q1. Okay, let me generate. We have two charges separated by what? Our distance, right? R in meter. Good. Now, Coulomb force says that force equals to what? Okay, Q1, Q2 over what? Over R squared. Now, I want to also know that Coulomb force is a vector force. Is a vector force. Is a vector force. In fact, every force are called, they are what? Vector quantity, meaning they have size and what? Direction. I say that the essence of Coulomb force is to determine the strength of the force of attraction or repulsion between 2 point charges, right? It measures the strength. It means it measures the magnitude or the size or the resultant of that force that exists between 2 point what charges, between 2 point charges. Now, after knowing that Coulomb force measured the strength, since Coulomb force is a vector force, that means this force must have direction, because vectors are those quantities that has size and what direction. A Coulomb vector force or Coulomb force is a vector force that has magnitude, right, which represent the strength, or the size, right, or the resultant, or the what? The resultant. Then it also have what we call direction. Now, majority of us, we are stuck here. This is all we know about Coulomb force. We all know how to find the size of Coulomb force, how to find the strength, how to find the magnitude of this force. But most of the time, we don't know how to find the direction. Because if I have a 2 point charge, there is always a pull towards, always the pull of the force towards a particular charge, or towards or against that particular charge. All right? Like I gave an illustration between the comb and the piece of paper. What we notice, the force of attraction was moves towards what? That of the comb, right? The comb already has negative charge, like I explained. When you rub the comb on your hair, the comb acquires a negative charge. Is that not negative charge? Like I explained before. Then the paper itself has a neutral charge, meaning the number of electrons and protons are the same. So as we bring these two objects together, what do you notice? The electrons here we arrange themselves, right? Or this negative charge here, the electrons here we knock off the electrons in this paper to one side, right? So the charge is here, both electrons and the proton will rearrange in a way that here becomes what? Positive, right? So those of you who just entered, make sure you go through the video from beginning. I explained this principle called induction. So when this happens, the electrons are being knocked off to one side of the paper, or they are rearranged. Then we have the proton here, right? Then between this is our distance of separation in meter, which is what we just did here. So the whole of this here represents, is more like saying this is the comb, right? This is what? The piece of paper. Do you get the concept here? So we can measure the strength of attraction or repulsion using Coulomb's law. Likewise, this, I can measure the strength of attraction. The strength of attraction using what? Coulomb's law. All I need to know is to know the value of this charge here and the value of this charge here. Then impute them. Our K is already given us 9 times 10 to the power of what? 9, right? Newton meter square per what? Coulomb square. Exactly. Now, if I can get the value of this charge and that of this charge, I can be able to measure the strength. But what about the direction? Obviously, we have seen that the direction is towards this comb, because the comb pulls the piece of paper. After rubbing the comb on your hair and you bring the comb closer to the paper tends to move upward, is attracted towards the comb, right? So it means that the direction of action is towards the comb. Now, in reality, just note that Coulomb force we know is KQ1, right? Q2 divided by what? R squared. times unit vector. This unit vector represents the direction of this force. It tells us if the force is acting towards charge 1 or acting towards what? Charge 2. For this case here, the force is acting towards the negative charge here, meaning if there's a pull towards this end. Is that clear? So for this unit vector represents whether the force is acting towards charge 1 or charge 2. They always tell you, find the resultant force on charge 1 or find the resultant force on charge 2. Let's say if you are given two charges and they said, find the resultant force on a particular charge, meaning that the action of force, the direction of action is towards what? Charge 1. Okay, so this represents what? Unit what? Vector. Now, this will now lead me into a concept called direction of action, which I want every one of you in this large class to pay attention, because I will not repeat most of these things again. Let's look at what we call direction of action. In Coulomb's law. The first case, we look at case 1. Case 1, I will look at what we call horizontal components of forces. If I have charge 1 separated by distance r, I have my charge 2 here. All right? And we are asked to find the resultant force on Q1. Number 2, find resultant force on what? On Q2. Now listen. If we are given 2-point charges separated by distance r in meter, and we have to find the resultant force acting on what? On Q1. Emphasis is placed on charge 1. The resultant force for the first one on Q1 is F1. It simply means find F1, which is the force on charge 1. Right? Like we saw between the comb and the piece of paper, the action of force or direction of action is towards the comb, right? So there's always a direction of action towards a particular charge. Towards what? A particular charge. If not, we will not be able to determine the direction of the Coulomb force, right? Okay, so our direction of action, force, our F1 rather, will give us, from Coulomb's law, we say that the law says what? F, right? Let me start with F equals to what? K, Q1, Q2 over what, yeah? R squared times unit vector. So here becomes F1 to find the force on Q1. The force on Q1 will give us F1, which is same as what? K, Q1, Q2 divided by what? By R squared times 1, 2. This is also same as 1, 2. When you see F1, I have 2-point charges, Q1 and what? Q2. And we have to find the force on Q1. This means F1, which is same as what? F12. F12 means the action of force. The action of force is from 2 to 1. Okay. For this, Now we have been able to define the force. This means F12. If I'm to find the resultant of force on Q2, what will it be? F21. F21, meaning from 1 to 2. So F12 means the action of the force is from 2 to 1. Is that clear? So the next is to define the direction of action. This sign means what? Unit vector. Unit vector shows what? It shows the direction of action. Okay? It means that where is the force acting towards? For this, since we are asked to find the resultant of the force on Q1, that means the force is acting towards what? Towards Q1. For number 2, we have to find what? The force on what? On Q2. It means that for number 2, the direction is towards what? Q2. So since we are asked to find the resultant force on Q1, which is same as what? F1, which is equals to what? F12, meaning from 2 to 1. Or something I can just use F1 to represent it. They're all the same. Now, but let's define the direction of action. That will also be what? Unit vector of what? 1, what? 2. Now, what we should start asking ourselves is that, how do we define the direction of action? We have to note that the direction of action arrow 1, 2 is from 2 to 1, meaning from 2 to 1 is minus I. I will explain. In vector, listen, we have vector can be represented in either 2 components or 3 components, right? But in Coulomb's law, Coulomb's law is a 2D vector. It's a 2D vector, all right? Meaning we have what we call the X, right? And what here? The Y. The S represents the I. The Y represents what? The J component. If this part represents positive I, what will be here? Negative I. If this part represents positive J, what will be here? Negative J. Now, since the direction of action is from 2 to 1, what does that mean? It is moving towards negative I. It's just like saying this is horizontal, right? We are dealing with I. This is my charge 1 here. This is my charge 2 somewhere here. And we are saying that the action of force is from charge 2 towards charge 1. So it's moving towards negative I. So that means my unit vector, okay, of R from 2 to 1 is what? Minus what? J. Okay. For this, number 2, find the resultant vector on charge 2. On charge 2 means from charge 1 towards charge 2. It means that my direction of action will not change, towards this side. It means from charge 1 towards charge 2. And from this to this is what? Positive I. So that means that unit vector of 2, 1 will be what? Positive I. Thank you. Okay. Will be positive I. All right, let's go. For number 2. Okay, let me finish up this. Therefore, F1, 2, which is same as F1, right? Is then equals to what here? KQ1, Q2 over R squared 1, 2 times minus I. And that will give us F12 equals to minus KQ1, Q2 over R squared 1, 2 times what? I. So this is the final expression that can be used to find the force on what? On Q1. All right? Where I represents what? The unit vector. Let's say if Q1 is positive, Q2 is positive. Definitely at the end of the day, our F12 will be what? Minus something. Let's say if I have my F12 minus 18I. Okay? That means our F12 modulus will be what? 18 Newton. Is that clear? Then if I'm to remove 18 from here, what is the remaining here is what? minus I. Minus I means towards the negative x-axis. So that means the size of this force becomes 18. The direction becomes towards the negative x-axis. Do you get the concept now? Now, but I'm just giving an illustration. So I will solve good example with this. Now let's move into, let's look at number 2. The resultant force on Q2. What do you think that will be? Number 2, we also find the force on what? On Q2. The force on Q2 is F2, which is same as what? F comma what? F21, right? Meaning from 1 to 2, which is same as 2. Right there. And that will give us what here? Our F comma F21 becomes what here? Okay, Q1 again, Q2 over R squared 2 comma 1 times unit vector of 1, 2 comma what 1. Already I've defined what this will be. Unit vector from 1 to 2 or 2 comma 1 is simply from 1 to 2 towards the positive x-axis, towards the positive x-axis. So that is I. That means our F2 comma 1 becomes what here? Okay, Q1 Q2 over what? R squared 2 comma 1 times I. Okay, please, if you are following, indicates that you are following. If you are following, please indicate that you are following. Please, if you are following, indicate that you are following. Now, let's move on. What if, let's look at what we have here. Still under horizontal, but in this case we have 3 charges. 3 charges. If I have 3 charges, I have Q1, I have Q2, and I have what? Q3. The distance between Q1 and Q2 is A. That of Q2 and Q3 is B. And we also find the force on Q1, on Q2, and what? On Q3. Okay. To find the force on Q1, meaning F1, in this case, we have 3 forces. There's a principle called superposition from the principle of superposition of forces. Okay, the sum of all forces, all forces acting on a particular charge is equal to the sum of the individual forces, okay, acting on that same charges. What I mean by that is that when you do the word principle of superposition of forces, and we also find the force on Q1, okay, from that principle, the force on Q1 is simply what? F1, okay? The principle is saying that since I have multiple charges, more than 2 charges, okay, the force acting on charge 1 is simply the force from Q2 to Q1 and from Q3 to what? To Q1. If I have 2 charges here, I have Q1 and I have what here? Q2. I'm to find F1. F1 means what? F12, right? Meaning from only 2 to what? To 1. If I have F2, F2 means what? F21, meaning from 1 to what? 1 to 2. But in this case, we have Q1, Q2, and Q3. And we have to find F1, the force acting on charge 1. That will give us what here? F12 plus what? F13. Meaning that the direction of action is from charge 2 to charge 1, then plus charge 3 to what? To charge 1. We call this one principle of a superposition of what? Of forces. Okay, now the next is to find F12. What is our F12? F12 is what? KQ1, Q2 over what? R squared 1, 2 times unit vector of what? 1, 2. Don't forget, I'm defining F12, meaning F12 means from 2 to 1, which is our F12 equals KQ1 Q2 divided by R squared 1, 2 times unit vector of 1, 2. Now let's define what that F12 is. What then is F12? F12 becomes what? K Q1 Q2 over R squared 1, 2 times. The direction of action is from 2 to 1. Let's define our direction now from 2 to 1. Let's see. From 2 to 1. This is still horizontal. Don't forget. This is still horizontal. We say that for horizontal, here is I. Here is what? Minus I. This is J. This is what? Minus J. This represents X. Still minus X, right? And all that. So from 2 to 1 is towards negative I. So what will be here is what? Minus I, which will give us minus I times the whole of this will give us what? Minus K1, KQ1, Q2 over R squared 1, 2 times I. Is that clear? Now let's find our F13. F13 will then give us what? KQ1, this case is between charge 1 and charge 3. F13 is between charge 1 and charge 3. But don't forget that the action of force is on charge 1. So that means from 3 to 1. From 3 to 1. Alright? From 3 to 1. So let's move on. That will give us what here? F13 is KQ1 Q3 over what? R squared 1, 3 dot unit vector of what? 1, 3. So that will give us what here? F13 equals to what? KQ1 Q3 over what? R squared 1, 3 dot minus I, because it is still towards negative I. Towards negative I. So this is same as minus KQ1 Q3 times I over R squared 1, 3. I hope you know why I put this minus sign here. This is like saying minus I, right? If I'm to rewrite this, the minus sign will be here, right? Will not be here. Here will be what? Here will be I. Then let's go. Our F1 becomes, so our F1 is the sum of F12 plus F13. What's our F12? F12 is simply KQ1 Q2 over what? R squared 1, 2 I. Alright? Minus KQ1 Q2 over R squared 1, 2, which is this. Then minus, I'm adding this expression, right? This expression with this, that will give us here minus what? KQ1 Q3 over what? R squared 1, 3 R. So what do you notice here is that we added our F12 is this, our F13 is this. But don't forget that the distance between R12 means what? From 1 to 2. The distance is what? Is A. So I can rewrite this by saying that F1 is equals to what? Minus what? K Q1 Q2 over R12 is A. So we have A squared, right? A squared I minus what? K Q1 Q2 I divided by our R13 means for 1 to 3, which is A plus B. A plus B all what? All squared. A plus B all squared. This is the final expression for F1. Okay, number 2. If we also find F2, resultant force on charge 2, meaning that emphasis is now placed on charge 2, no longer on charge 1. So that means that from the principle of superposition of forces, our F2 becomes what? F21 plus what? F23. F21 plus F23. Meaning to find the force on charge 2, it means that the action of force will be from charge 1 to 2, then from charge 3 to 2. Do you get the concept? From charge 1 to 2, we are going towards positive I. From charge 3 to 2 towards negative. Okay, so let's define. Let me just put the entire value there so we can just move on. Our F2 becomes what here? Our F21 will be what? KQ1 Q2 divided by what? The distance between charge 2 and charge 1 is what? Is A. So over what here? A squared. So what is our direction of action? Is that we are moving from 1 to 2. From 1 to 2 is towards positive, meaning I'm going this way. From 1 to 2 is positive I. What here is what? I, right? Plus, then let's define F23. That will give us what here? KQ2, Q3. F23 is between charge 2 and charge 3. So the charge will be what? Charge 2 times what? Charge 3 divided by what here? Let's go on. Divided by the distance between charge 2 and charge 3 is B. What B here is what? Is B squared. But let's see. What will be the direction of action between from charge 3 to charge 2? From charge 3 to charge 2, the direction of action is towards this side, right? Now give us minus I, minus I. So here we're going to have where here as what? Minus I. Do you get the concept now? But minus I times plus should give us minus. So what should we do here? Here becomes what? Plus, right? Here becomes what here? Minus. Let me repeat. Let me just put this here as plus and here as minus. From 3 to 2 is minus. So final expression becomes, our final expression becomes, this becomes F2 equals to what? KQ1, Q2 over what? A squared minus what? KQ2, Q3 over what? B squared I. Here we also have what here? I. Final formula to find F2. Is that clear? Now the next one is we are dealing with 3 charges. Q1, here we have Q2, and we have what? Q3. Here is A and here is B. To find the force on Q3, meaning F3. F3 will give us what here? F31 plus what? F32. F31 plus F32, meaning from 1 to 3, then from 2 to 3. F31 means from 1 to 3, from 2 to 3. So let's define F31. So F3 becomes what here? K, Q1, Q3 is between charge 1 and charge 3 divided by distance between charge 1 and charge 3 is A plus B. So I have A plus B, all what here? All squared, right? So the direction of action is simply from 1 to 3. 1 to 3 is positive I, right? Good. Plus F23. That will give us KQ2, Q3 is between charge 3 and charge 2 divided by what? Distance between charge 3 and 2 is B. So divided by B, B squared. So the direction of action will be from 2 to 3. From 2 to 3. Still towards positive. This is the formula for this. All of this is the same thing for vertical. I will just pick one example under vertical, then we move into something else. Okay. Now let's look at vertical. I'm not going deep into this because they are all the same concept. If I have charge 1, I have charge 2. And let's say I have charge 3. And distance between charge 1 and charge 2 is A. Distance between charge 3 and charge 2 and charge 3 is B. And we have to find F1. Let me find F1 and F2. Okay? By now you should know what F1 represents. F1 means find the resultant force on charge 1, right? On charge 1. That is what it means. So F1, from the principle of superposition of force, F1 is simply what? F1, 2 plus F1, 3. Is that clear? Meaning that the action of force is on charge 1. So that will give us from 2 to 1, from 3 to 1. Is that clear? F1 is from 2 to 1, from 3 to 1. Okay? But if I have Q1 and just Q2, and we have to find only F1, this is just between two charges, right? What is your F? What will be our F1? F1 will be what here? The same as F1, 2, meaning from only 2 to 1, because we only have 2-point charges in a system. So if I'm to find the force acting on charge 1, it simply means F1, which is what F1, 2. But if I have three charges, I'm to find the force acting on charge 1. It means I have to bring up the principle of position of force. And that will give us F1 equals F1, 2 plus F1, 3. For this is simple. It means my F1 here is what? Is K, Q1, Q2 over what? R square times unit vector of 1, 2. Is that clear? And 1, 2 means from 2 to 1, meaning I'm going upward. And upward means what? Positive J. Is that clear? Positive J. This means what? Downward means negative what? J. So the direction of action from 2 to 1 is plus J. So what will be here is what? Is J. Is that clear? Okay. So I just have to bring this out for you guys to take notes. You can also have vertical between two charges, not just between three charges. So for this, let's define this. Our F1 becomes what? F1, 2. F1, 2 will give us what? K, Q1, Q2 over distance between charge 1 and charge 2 is A. That will give us what? Yeah, A squared. So the direction of action is from charge 2 to charge 1. Charge 2 to charge 1 is upward, we are going up, which is positive J. Okay, so plus F1, 3 is simply what? K, Q1, Q3 over. Now between charge 1 and charge 3, the sum of the distance is A plus B, meaning from the direction of action is from charge 3 to charge 1. So we are covering two distances. We have A and B. So that will give us what here? A plus B all was squared times J. Why are we doing times positive J? Because the action is towards positive y-axis, which represents positive J. So we have gotten the formula for this. If we have to find F2, F2 will now be what? F21 plus what? F23. F21 plus F23. So our F2 will then give us what? K, Q1, Q2 over R square 1, 2. Okay, let's just go straight. This time between charge 1 and charge 2 is A, which is our 1 and 2, is A squared. Okay, now the next is to determine the direction of action. This is from 1 to 2. 1 to 2 means we are going downward, which is negative J. Cartesian diagram we have here as negative J, positive J, right? So we are going towards negative J. So what will be here is what? Negative J. All right? So plus F23 will give us what here? K, Q2, Q3 over between charge 2 and charge 3. Between charge 2 and charge 3 is B. So we are going to having b squared here. Distance is b. So from 3 to 2, 3 to 2, we are going up. In this case, we are going towards positive j. From 3 to 2 means we are going towards positive j. And that'll give us what? J. So let me rearrange this. My F2 becomes what? Minus times plus give us minus, right? KQ1, Q2 over A squared, right? Plus KQ2, Q3 over what? B squared, J. Is that clear? So this is just how to find the same principle used in finding that of horizontal is also used for vertical. It's also used for vertical. All right, so just excuse me a little. All right, so let's finish up. The next is if we have an inclined plane, or if two charges are placed along an incline. Let's say I have a charge here, Q1 and Q2, right? Let's say I have a plane. I have my first charge, Q1, and I have another charge here, Q2. Then distance between, I have a distance here, A, and here's what B. And we also find the resultant of F1, meaning find the force acting on charge 1, right? Now, anytime you see F1, it means on charge 1, F2 means on charge 2. We have only two charges here placed along this plane. Okay, so the first thing we need to do is that we have to get their distance first. This is the distance here. This is an hypotenuse line, right? So for me to find the distance, since this is a right angle triangle, we use what we call Pythagoras theorem to find the distance. So let's call here R. So using Pythagoras theorem, that will give us what here? R squared equals to A squared plus what? B squared. So R becomes square root of what? A squared plus B squared. So the distance between charge 1 and charge 2 is given as A squared plus what? B squared, all square roots. Is that clear? Okay. Now the next is to find F1. Don't forget that I said if we are dealing with two charges and they say find F1, F1 is same as what? F comma what? F1, 2. Is that clear? And that will give us what? Okay. Q1, Q2 over R squared 1, 2 times unit vector of 1, 2. All right. Now, but the major thing is now that how do we define the unit vector? Of course, if you look at this, charge 1 and charge 2 is along an inclined plane. And the inclined plane here, we got this is a hypotenuse line by adding the vertical and what? The horizontal together. So whenever we have an inclined plane, what comes to your mind is two dimension. It means that I'm going to get my unit vector in 2 dimensions. I'll bring out the vector, then also bring out the unit vector of that vector. Is that clear? Now, how do we do that? Just pay attention. Already we know that F1 is F12, which is KQ1, Q2 over R squared, right? 1, 2. 1, 2 means distance between charge 1 and charge 2. Don't forget, this means distance between charge 1 and charge 2. And the distance we have defined using Pythagoras theorem as r equals to what? Square root of a squared plus b squared. The challenge is, how do we define the direction of action? Now, how do we find the direction of action? It's very simple. Direction of action of 1, 2. Listen, 1, 2 simply means from 2 to 1. From 2 to 1 means I will move down this way, then move towards charge 1. If they say from 1 to 2, it means I'll move from charge 1 this way and move upward. Since I'm looking for direction of action from charge 2 to charge 1, the action of force is on charge 1. So that means charge 2 is being pulled towards charge 1. But the pulling can never occur along this plane. It can only occur along this line here. So the action of force will move from this region, get to this edge here, then move towards this direction. So it means I'm moving this way, then also moving this way to this point. Is that clear? Now let's go. And that will give us, when we move this way, it means I'm moving vertically downward. Don't forget that in the Cartesian diagram, this is our minus j. This is what? Our j. This is what? Our I. This is what? Our what? Minus I. This thing represents y, This is what? Minus y. This represents what? X. This is what? Minus x. Is that clear? So if I'm moving down, this is along the vertical axis. It means I'm going towards negative j. It means I'm going downward, right? First, when you get to this part here, we then move toward this region. It means that I'm now moving towards what again? Negative what? I. So this region means negative j, negative I. Negative j, negative I. But if I'm moving from 1 to 2, if I'm to find arrow to 1, meaning from 1 to 2, that means what? I'll move towards this region, right? Positive I, positive I, positive j. Positive I, positive j. But since our action is on charge 1, so that means that the direction of action must move from charge 2, then towards charge 1. Charge 2, negatively, then charge 1, negatively, negative I. Now let's go. While moving downward, we move across B, right? So this will give a minus j. That minus j times b is what? Minus bj. Don't forget, minus bj. We move downward, right? Negative j. Then multiply the negative j by b. That will give us what? Minus bj. Then when we get to this point, this terminal, we move towards charge 1. Because the action of force is towards charge 1. And that will give us negative I. Negative I times A is what? Negative what? AI. Negative AI. Is that clear? Now I've defined the vector. The vector R. The vector R is what? Minus BJ minus AR. Don't forget that in vector, there's a topic we learned last semester, which is called unit vector. Right? Unit vector is still the same. This is called unit vector, right? It means arrow cap. Is that clear? When you see a symbol like this, that means unit vector. But what I just defined here is just a vector. If I have a vector, let's say vector A, this vector A, to be equals to SI plus YJ, like we have here. This is like saying minus AI minus BJ, right? And I'm to find the unit vector. Unit vector is defined as vector A over what? A modulus of A. Meaning that vector A is this, SI plus what? YJ over. Modulus of A is simply square root of what? Of S squared plus what? Y squared. I'll repeat again. If vector A is this, by definition, unit vector of A means vector A over A modulus. Meaning I will repeat vector A, then divided by what? A modulus, which is square root of x squared plus y squared. So for this, have I defined my vector? This is my vector, right? Then this will now be what? Over square root of minus a all squared plus what? Minus b all what squared. We then rearrange this proper because in your 3D, I must come first before what j. And that will give us what? Minus ai minus bj divided by what? Square root of minus a all squared is same as what? A squared minus b all squared is same as what? B squared. So that means that the direction of action from chart 2 to chart 1 is simply this. I hope there's no challenge here. And some of you have issues with this kind of mathematics. If we have minus a all to the power of 2, this is same as minus a times minus a, right? Minus times minus is plus. What is a times a? Is a squared, which is same as this. The same also goes with what? Minus b all to the power of what? 2. That means that, therefore, our F1 is now equals to what now? Let's define it together. KQ1, Q2 divided by what? R1 to distance between charge 1 and charge 2 is this. Is that not? Is square root of a squared plus b squared, meaning square root of what? Of a squared plus what? B squared. All square. Don't forget, all square. Distance, R1, 2 is just this. But we have square here, so I have to put the square. Times unit vector of R, unit vector from 2 to 1. What we have? We have this, right? Minus AI minus BJ divided by what? Square root of what? Of A squared plus what? Plus B squared. Square can cancel square root from here. If that should occur, this will give us F1 to be equals to what? KQ1, Q2 divided by what? A squared plus what? B squared times minus AI minus BJ divided by A squared plus B squared all to the power of what? Half. This is times, right? We are multiplying them. Square root of this is same as A squared plus B squared all to the power of half. Meaning the same thing with this law of indices, right? Power law of indices. Now, what do we do next? Let's finalize. These two they have the same parentheses. We have a squared plus b squared. The power is 1. The power is what is half. When two bases have the same, when we have similar base, we can pick one base, right? And add what? The power. The power here is simply 1. So here will now give us what here? F1 equals to what? KQ1, Q2 times minus AI minus BJ all divided by A squared plus B squared all to the power of 3 over 2, right? If the power is 1 and yes, half, meaning I'm going to add all the power, 1 plus half. That will give us what? The LCM is 2. Here will give us 2 plus 1, which is 3 over 2. So we can stop here. You can equally stop here as a final formula, then solve, right? I'm just simplifying further, okay? Just showing us some formula and all that. Now, The last aspect on this, then we'll move into one or two examples, then I will end this class for today. The last aspect on this, we're almost rounding up. The last aspect on this. Okay, let's look at the last aspects. What if we have thin and inclined plane? But in this case, we have charge 1, charge 2, and we have charge 3 here. We still have our distance R. We have here as A and here as B. Like I said, the first thing we need to do is to find a distance. Distance between charge 1 and charge 3 is A. Charge 2 and charge 3 is what? Is B. But charge 1 and charge 2 is unknown. We don't know it, right? It's unknown. So let's find distance between charge 1 and charge 2 using Pythagoras rule, right? Pythagoras rule of theorem. That will give us what? Let's go. R squared plus A squared plus what? B squared, right? And the square of the hypotenuse plus the sum of the square of what? Adjacent plus that of the opposite, which is A squared plus B squared plus R squared. So that means here R equals to square root of what? Of A squared, right? A squared plus what? Plus B squared. Exactly. A squared plus B squared. Now the next is, if we are now asked to find let's say F1, I will just look for F1 and F2. I will solve for, let's solve this time around. Let's find F2. Find F2. Okay. Okay, to find F2, we call that according to superposition of forces, F2 becomes what? F21 plus what? F23. Don't forget, F21 plus F23. Meaning, to find the force acting on charge 2 simply means the sum of the force from charge 1 to what? To charge 2. Then from charge 3 to what? To charge 2. Is that clear? Okay. So the first thing we need to do is to find our F2, 1. F2, 1 is simply KQ1, Q2 over R squared 1, 2 dots unit vector of 1, 2. Is that clear? Okay. Now let's define our unit vector. Unit vector of 1, 2 in this case is from charge 2 to charge 1. Like I've said, if I'm to take my direction of action, it will not be along this plane, right? I will go this way, then move this way. It means I'm going towards negative, of course, from 2 to 1. Let me confirm. F21, from 1 to 2, sorry. Not from 2 to 1. From 1 to 2. All right, sorry. From 1 to 2. From 1 to 2. Sorry. From F2, 1. F2, 1. Oh, okay, I hope that is clear now. So we're dealing with F21. F21 is from 1 to 2. So from 1 to 2 means we are moving this way, then this way. Is that clear? So moving this way means from the Cartesian diagram, we have plus I, minus I, we have J, and minus J. Meaning we are moving towards positive I and positive J. This way means positive I. This way means positive J. So let's move. That will give us, from this region, positive I, right, times A is AI plus upward positive J times B will give us what? BJ. All divided by, then it will give us square root of what? A squared plus what? B squared. So that means our F2, 1 becomes what? KQ1 Q2 over distance between charge 1 and charge 2 is this, Abi. And the value of R, we have defined R as what? Square root of what? Of A squared plus what? Plus B squared. Right? A squared plus B squared. And that will give us what? Yeah? Root of what? A squared plus B squared. All what? Yeah? All squared. Times. Unit vector we define is this, right? Times AI plus BJ divided by square root of what? A squared plus B squared. Square can cancel square roots. So F21 becomes what? Okay, Q1, Q2 over A squared plus B squared. Then times what? Times AI plus what? BJ divided by what? A squared plus B squared, all to the power of what? Half, right? So these two can multiply each other, and that will give us what? Like we did in the previous example, F2, 1 becomes what? Okay, Q1, Q2 over what? So times AI plus BJ, all divided by what? A squared plus B squared, all to the power of 3 over 2. The power here is 1, Abi. So 1, if I'm multiplying this with this, I'll pick the common base, then add up 1 plus 1 over 2. That will give us 3 over 2. Or we can just stop here, right? Okay. Now, we have only gotten F21. The principle says F2 equals to F21 plus F23. The next is to find F23. What's our F23? From 3 to 2. That is very simple. Meaning along the vertical axis only. Along the vertical axis only. So let's define that. Along the vertical axis only. Before we started incline, we first of all discuss along the horizontal axis, along the vertical axis. If I'm to find my direction of action from 3 to 2, what will be the result? Positive J only. Don't forget, you have to find my direction of action from charge 1 to charge 3 only. What will be the answer? Is positive I. From charge 3 to charge 1 is negative I. We have, please go back, those of you who just came in, go back, go through the videos again from beginning. We talked about direction of action, horizontal and vertical, before we come into incline. Because what I'm saying that is that from chart 3 to chart 2 is just along the vertical. It means I will consider just what? J as my direction of thought of action. Don't forget. So let's go. So F23 becomes what? KQ2 Q3 divided by distance between 2 and 3. 2 and 3 is B. So I will have what here? I will have just B squared. Is that clear? So direction of action is from charge 3 to charge what? 2. What over here is J. Is that clear? Or I can still use the concept here. The concept here says I have to find the vector first, right? Then find the modulus of the vector. Then divide the vector by its modulus to get the unit vector. This unit vector here, if I'm going from 3 to 2, which is J, J times B is what? Is BJ. Is that clear? Is BJ, right? Now, unit vector of this is what? Vector, this vector, right? Over modulus of what? Of this. Modulus of BJ is what? Is simply square root of what? Square root of what? Of B squared. Is that clear? So square can cancel what here? Square roots. Remaining what? BJ over B. B can cancel B. Remaining what here? J. I see it's still the same thing. Even if you have to go through this process, it's still the same thing. But I made it simple in a way that along the vertical, just consider J components. So from chart 3 to chart 2, the direction of action is towards what? Is towards chart 2, right? Which is positive J. If we are looking from chart 2 to chart 3, what will be the result? negative j. So let's just move on to that. Now we have seen, okay, then therefore our F2, don't forget F2 is what? F2 comma 3 plus F2 comma, so F2 comma 1 plus F2 comma 3. Is that clear? Our F21 is simply this. So that means that will give us what here? Let me just clean this side. Bring out the final expression. Our F2 becomes what? Our F2 becomes, our F21 is this, which is KQ1 Q2 times AI plus BJ divided by A squared plus what? B squared to the power of what? 3 over 2 plus our F23 is simply KQ2 Q3 J divided by B squared. Final expression. Final expression. Please don't forget this, okay? Final what? Expression. Okay, I'm going to stop here for tonight. Then we have a diagram like this. We have our charge 1, we have charge 2, and we have charge 3. Then distance between, we have a distance here. From here to here is A, from here to here is B. And we have to find the force acting on charge 1 and charge 2. The force acting on charge 1 and charge 2. So please make sure you solve this and submit your answer in the comment section, alright, of this video. Please put your answer in the comment section of this video. Alright, so tomorrow we continue. I'll be solving real example tomorrow. All we just learned today is the general concepts. So by tomorrow I will solve real example. I want to bring some past questions. We'll solve them tomorrow on Coulomb's law, and also how to find the action of a force over another force. So see you guys tomorrow, the same time by 8 p.m. Alright? Then if you have any question you want to ask, you can drop the question in the comment section. Alright, thank you guys. See you tomorrow in my class.